Let's look at an example of a collision in one dimension. Ball 2 is at rest, and ball 1 is moving toward it with a velocity of 6 meters per second. Ball 1 has a mass of 0.32 kilograms, and ball 2 has a mass of 1 kilogram. The two balls collide elastically. No external forces act on the balls. What is the velocity of each ball after the collision? Okay, what are we given? Ball 1 has a mass of m1 equals 0.32 kilograms, and ball 2 has a mass of 1 kilogram. Before the collision, ball 2 is at rest, so the initial velocity of ball 2 is equal to 0. Ball 1 is moving toward ball 2 with a velocity of v1 initial. Let's assign the positive direction to be to the right. That makes v1 initial equal to a positive 6 meters per second. And what are we looking for? We're looking for the velocity of each ball after the collision. So we're looking for v1 final and v2 final. Since we have two unknowns, we need two equations now. There are two clues in the problem that can lead us to these two equations. The first is that the two balls collide elastically. An elastic collision means that the total kinetic energy of the system before the collision is the same as the total kinetic energy of the system after the collision. The second clue we're given is that no external forces act on the balls. Remember that if the work done by non-conservative external forces is 0, then the total linear momentum of the system before the collision is the same as the total linear momentum after the collision. So let's find an equation to use from this first condition. Total initial kinetic energy equals total final kinetic energy. So the initial kinetic energy of ball 1 plus the initial kinetic energy of ball 2 equals the final kinetic energy of ball 1 plus the final kinetic energy of ball 2. Kinetic energy equals 1/2 mv squared, so we'll substitute the appropriate terms for each of these kinetic energies. Since we're working with a one-dimensional collision, we'll leave off the vector arrows from the terms and rely on the positive and negative signs for direction. Since v2 initial is equal to 0, this whole term is equal to 0. We can also cancel out the 1/2 terms. Now we're looking for v1 final and v2 final, so let's solve this equation for v1 final. We'll do this in a couple of steps. And for now, we'll actually just leave it in terms of v1 final squared. So this is our first equation. For this equation, we know m1, m2, and v1 final, v1 initial, but we don't have v2 final yet. So now we'll use this second condition to find another equation. Total initial linear momentum equals total final linear momentum. So the initial linear momentum of ball 1 plus the initial linear momentum of ball 2 equals the final linear momentum of ball 1 plus the final linear momentum of ball 2. Linear momentum is equal to mass times velocity, so we'll put that in for each linear momentum term. Since v2 initial equals 0, this term is equal to 0. Now we need to solve this equation for v2 final. We'll do this in a couple of steps. And now we have our two equations for our two unknowns. Now we'll combine these two equations to first find v1 final. So first we substitute our equation for v2 final into our equation for v1 final squared. Then we'll take some steps to simplify this expression a bit. We'll gather terms to put the expression in quadratic form for v1 final. Now we can plug terms into the quadratic equation. And choosing the negative sign in the numerator, we can simplify to this expression. As you can see, it takes a fair bit of algebra to get to this expression, But the good news is that this is the general form of the solution for a two-body elastic collision, where object 1 has an initial velocity and object 2 is initially at rest. So you can just remember this expression for the future. Just make sure that if you use this form, you keep object 1 and object 2 consistent, where object 2 is initially at rest. Next, we can plug in our values for v1 initial, m1, and m2. And now we can use our calculator to solve, getting a value of minus 3.09 meters per second for the final velocity of ball 1. The minus sign means that ball 1 moves to the left after the collision. This seems reasonable since the mass of ball 1 is about 1/3 the mass of ball 2. Now that we have a value for v1 final, we can plug it into our expression for v2 final, along with our values for m1, m2, and v1 initial. And using our calculator, we get a value of 2.91 meters per second for v2 final. This means that ball 2 moved to the right after the collision. This is the classic example of a one-dimensional elastic collision problem, and you can use it as a guide when working other problems.